A 10 million cell mesh, 3 weeks of setup, and the simulation diverges after 12 iterations because of a single degenerate cell. Mesh quality is the silent gatekeeper of every CFD simulation. Get it wrong and no turbulence model, no solver trick, no amount of computing power will rescue your results. In the next 9 minutes, you will understand the three metrics that separate a reliable mesh from a ticking time bomb: skewness, orthogonality, and aspect ratio. And later, I will show you why one of these metrics is perfectly fine to violate, if you know where. Before we define any metric, you need to understand what the finite volume method assumes about your cells. Every time the solver computes a flux across a face, it interpolates field values from the two neighboring cell centers. That interpolation assumes the face center lies roughly on the line connecting those cell centers. Every time it computes a diffusive flux, it approximates the face normal gradient using the difference between the two cell center values. That only works if the cell to cell vector is aligned with the face normal. And every gradient reconstruction, whether green Gauss or least squares, assumes cells are reasonably shaped and similarly sized. Break any of these assumptions and you introduce error. Break them badly and the solver cannot converge at all. Skewness measures how far a cell deviates from its ideal shape. For a triangle, the ideal is equilateral, all angles at 60 degrees. For a quad, it is a perfect square, all angles at 90. The standard definition is equiangle skewness. You take the largest angle in the cell, subtract the ideal angle, divide by 180 minus the ideal angle. Then you do the same for the smallest angle. Whichever ratio is bigger, that is your skewness. A perfect cell scores 0. A completely degenerate cell scores 1. Here is the intuition. Imagine predicting the temperature at a doorway by averaging the temperatures in two adjacent rooms. If the doorway sits centered between the rooms, the average is reliable. But if the doorway is offset far to one side, highly skewed, your average becomes unreliable. That is exactly what happens to face interpolation on a skewed mesh. So, what number should you actually target? For tetrahedral meshes, keep maximum skewness below 0.95 and ideally below zero point 0.9. For hexahedral meshes, tighter, below 0.85. Your average skewness should sit below 0.33. But here is the trap most engineers fall into. They look at the average and declare the mesh is fine. A mesh with 99.99% excellent cells and a handful of degenerate cells near a sharp corner will still crash. Always check the maximum, not just the average. In OpenFOAM, run checkmesh. In Fluent, check the skewness histogram. Those were cells. That is where your simulation lives or dies. Orthogonality, or more precisely non-orthogonality, measures the angle between the cell to cell vector and the face normal. On a perfect structured grid, these two vectors are perfectly aligned, 0 degrees non-orthogonality. But on unstructured meshes, especially around curved surfaces and sharp corners, these vectors diverge. Why does this matter? The diffusive flux across a face requires the gradient normal to that face. On an orthogonal mesh, that gradient is simply the difference of the two cell center values divided by the distance. On a non-orthogonal mesh, this simple approximation no longer points in the right direction. You need a correction term, and that correction becomes unstable above around 85 degrees. Think of it like measuring the slope of a hill going north. If your only measurement line runs northeast, you have to subtract out the eastward component. The further your line deviates from north, the more error creeps in. Below 40 degrees, no issues. 40 to 65 degrees. Standard discretization schemes handle it fine. Between 65 and 75, you should consider adding non-orthogonal correctors in OpenFOAM. Above 75, you need them. Above 85 degrees, the mesh is essentially broken. No reasonable number of correctors will fix it. And here is the critical insight. At 90 degrees non-orthogonality, the finite volume scheme is no longer conservative. That fundamental property, the reason we use finite volume methods in the first place, simply vanishes. In Fluent, check orthogonal quality instead, it is the cosine of the non-orthogonality angle, ranging from 1 for perfect down to 0 for degenerate. Keep it above zero point 0.1 as an absolute minimum, but aim for above zero point 0.7. Aspect ratio is the ratio of a cell's longest dimension to its shortest. An ideal isotropic cell has an aspect ratio of 1. Stretch it and the ratio climbs. High aspect ratio means the cell resolves gradients well in one direction but poorly in others. This creates anisotropic truncation error. If unexpected gradients develop in the long direction, they get smeared out. Numerical diffusion. For multigrid solvers, extreme aspect ratios create ill-conditioned matrices that slow convergence dramatically. But here is where most engineers get confused. High aspect ratio is not always bad. In boundary layers, gradients are steep normal to the wall and gradual along it. A prism cell with an aspect ratio of 50 to 1 is not a defect. It is exactly what the physics demands. Think of it like pixels on a screen. Square pixels are ideal for capturing detail in all directions. But if your image only has horizontal stripes, tall rectangular pixels capture it perfectly, and you need far fewer of them. Here is the key insight that ties everything together. Skewness primarily corrupts convective fluxes. When cells are distorted, gradient reconstruction fails, and upwind schemes lose their accuracy. The result? Artificial smearing of flow features, numerical diffusion on the convection terms. Non-orthogonality primarily corrupts diffusive fluxes. The Laplacian approximation breaks down when the cell-to-cell vector misaligns with the face normal. In segregated solvers like Simple or PISO, this directly destabilizes the pressure equation, causing mass conservation errors and pressure oscillations. Aspect ratio creates directional bias. Excellent resolution in one direction, poor in another. Each metric attacks a different part of the discretization, and they compound. A cell that is simultaneously skewed, non-orthogonal, and stretched will fail in every possible way at once. Not all cell types handle quality equally. Hexahedral meshes are the gold standard. Naturally low skewness, excellent orthogonality, and they can stretch to high aspect ratios without degrading. The catch? They are brutally difficult to generate for complex geometry. Tetrahedral meshes are the opposite, automatic generation for any shape, but they cannot be stretched without destroying the skewness. They need 5 to 10 times more cells for equivalent accuracy, and they introduce more numerical diffusion. Then there are polyhedral cells, arguably the best compromise. Each polyhedron has 10 to 14 faces, giving far more neighbors for gradient reconstruction. They are less sensitive to stretching, need roughly 4 to 5 times fewer cells than TETs, and converge faster. If your measure supports polyhedra, you should seriously consider them. And for boundary layers, always use prism layers. They maintain wall normal orthogonality while allowing the streamwise stretching that the physics demands. Mistake 1. Checking averages instead of maximums. Your mesh histogram looks beautiful, but 5 cells with the skewness above 0.98 will crash the solver. Always check the worst cells. Mistake 2. Highest skewness in the boundary layer. High aspect ratio near walls is correct, but highest skewness is catastrophic. It corrupts wall shear stress and heat transfer predictions. Mistake 3. Abrupt size transitions. Jumping from fine to coarse with a growth ratio above 1.3 creates a local first order accurate zone that smears flow features. Mistake 4. Trusting solver tuning to fix bad meshes. Dropping to first order upwind or having under relaxation might achieve convergence, but the results are unreliable. The fix is always the mesh. Mistake 5. Skipping grid convergence studies. Good quality metrics are necessary but not sufficient. You still must demonstrate that refining the mesh does not change your answer. In OpenFOAM, the checkmesh utility is your first line of defense. It reports maximum non-orthogonality, maximum skewness, maximum aspect ratio, face interpolation weights, and volume ratios. Failed cells get written to sets you can visualize in ParaView. The mesh quality dict controls the thresholds. max non-ortho at 65 degrees by default, max internal skewness at 4, max boundary skewness at 20. In ANSY's Fluent, the mesh quality panel gives you orthogonal quality and skewness histograms with color-coded ranges. You can select and highlight cells below any threshold, incredibly useful for hunting down problem regions. Regardless of your tool, the workflow is the same. Generate the mesh, check the metrics, fix the worst cells, and repeat until every cell passes. Never run a simulation on a mesh you have not inspected. Let us bring it all together. Skewness measures cell distortion. It kills gradient accuracy and smears convective fluxes. Keep maximum skewness below zero point 0.9 for TETs, 0.85 for hex. Non-orthogonality measures the misalignment between cell vectors and face normals. It destabilizes diffusion terms and the pressure equation. Keep it below 65 degrees without correctors and never above 85. Aspect ratio measures cell elongation, harmful in isotropic regions, but perfectly correct in boundary layers where the physics demands anisotropic resolution. Every one of these metrics affects a different part of the discretization, and they compound near geometric singularities. The takeaway is simple: check your mesh before you check your physics model, because if the mesh is wrong, everything downstream is wrong too. Thanks for watching CFD Toolbox. If you want more CFD content, hit subscribe and check out my other videos on the channel.